Okay, one of the key assumptions of OLS is that the variance of our residuals conditioned on our x variables is constant. And this assumption is called homoskedasticity. So what this means is, if we have, say, a model like this model, what we are saying here is that our residuals do not depend on this variable x1. So if we draw a graph of these residuals, no matter if we measure the residual here or here, it is equal. But if this assumption is not met, then the variance of these residuals conditioned on x variables is a function of x itself. For example, if we have a model of saving as a function of income, then our OLS assumption is that the residuals do not depend on income. But we know that people at the lower end of income, they do not have many options. Hence, their saving is low, and also there is less variation of the saving between individuals. But as the income of individuals increase, so at the other end of higher income, that is people with very high income, they have more options. So some of them may be saving a lot more than average, and some of them may be saving less than the average. People with very low income, they don't have many options, so on average their saving is very close to the average saving in our sample. So this scenario is telling us that the variance of our model, it is a function of income itself. So this problem is called heteroskedasticity, and we know that heteroskedasticity is problematic in the OLS, although the beta coefficients or these coefficient values that we will get from our model, they are still unbiased and consistent under heteroskedasticity, and the interpretation of R squared is also unchanged. But what this heteroskedasticity does is that it invalidates our variance, and we know that both our f-test value and t-test value, they are based on the variance, which means under heteroskedasticity we cannot use statistical inferences to test for the statistical significance of any variable using t-test or f-test. And in the presence of heteroskedasticity, OLS is no longer a blue estimator. That is, there may be some other estimators, those may be more efficient than OLS, and we'll look at one estimator which is weighted least square, and we know that this is more efficient than OLS because it provides us with minimum variance. And this is what we are going to do in this chapter. We're going to look at heteroskedasticity, and first I'm going to introduce you to robust standard errors to make robust inferences for OLS, and then we'll look at how to test for the existence of heteroskedasticity in a model. We'll talk about Broish-Pagan test and white test, and then we'll talk about weighted least squares in two scenarios. In first, we'll know the exact nature of heteroskedasticity in a model, and in the other scenario, we'll not know the exact nature of the heteroskedasticity, and in that scenario, we will use the feasible general least square method. So this is the goal of this chapter, to talk about how to take care of this problem. Alright, I'll see you in the next video. Bye bye.